Hi friends, welcome back on our YouTube channel. Here I am with another lecture of classical mechanics. Today in classical mechanics we will discuss about Lagrangian formulation in generalized coordinate. So in the current lecture we will discuss about Lagrangian formulation in generalized coordinate, degree of freedom and generalized coordinate. Now, Lagrange's formulation in generalized coordinate. First of all, we will discuss about change of notation. For it, we consider a system of n particle. We generalize the Cartesian coordinate and mass in this n particle system. For particle number 1, the coordinates are x1, y1, z1, and since mass of first particle is m1, so m1, m1 and m1. In generalized coordinate, we write x1 as x1, y1 as x2 and z1 as x3, and mass corresponding to it is m1, mass corresponding to it is m2 and mass corresponding to z1 is m3. Now for particle number 2, coordinate was x2, y2 and z2. In generalized way, we will write x2 as x4, y2 as x5 and z2 as x6. The mass corresponding to x4 is m4, mass corresponding to x5 is m5 and mass corresponding to x6 is m6. In the same way, if we take particle number n, then its actual coordinate was xn, yn and zn. Now, in generalized coordinate, we write Zn as x3n, yn as x3n minus 1 and xn as x3n minus 2. Now, mass corresponding to x3n minus 2 is m3n minus 2. Corresponding to x3n minus 1 is m3n minus 1 and the mass corresponding to x3n is m3n. In this way, we generalize the Cartesian coordinate and mass for a system of n particle. Now, the nth particle has Cartesian coordinate and mass as x3r minus 2, x3r minus 1 and x3r, and mass m3r minus 2, m3r minus 1 and m3r. So, these are the Cartesian coordinate for nth particle and these are the masses for nth particle. Now, D'Alembert's principle was sigma j equals to 1 to n fj applied minus pj dot delta rj equals to 0 for n particle system. In generalized way, we will write this D'Alembert principle as sigma I equals to 1 to 3n fi applied minus mj d2 xi upon dt2 dot delta xi equals to 0, because pj dot was actually rate of change of linear momentum and rate of change of linear momentum is applied force according to Newton's second law. So this will be F and F is equal to ma, that is m d2x upon dt2. So this Pj dot is replaced by mi d2xi upon dt2, because here we use sigma I equals to 1 to 3n. So D'Alembert's principle, which is actually this one, will be this in Cartesian coordinate and mass in generalized system. Now, Lagrangian equation of first kind is mj rj double dot minus fj applied minus sigma I equals to 1 to k lambda I del hi upon del rj double dot equals to 0, and this will be mi d2xi upon dt2 minus fi applied minus sigma r equals to 1 to k plus k dash lambda r del hr upon del xi double dot equals to 0. Here, this k is actually total number of holonomic constraints, and this k dash is actually total number of non-holonomic constraints. So, Lagrangian equation of first kind will be this one. Now, this was Lagrangian's equation of motion of first kind. Thus, there are 3n differential equations, because here sigma I equals to 1 to 3n. So, there are 3n differential equations, each containing a maximum k plus k dash plus 2 terms. Also, here k plus k dash equations of constraint. Thus, 3n plus k dash equations are to be solved for 3n unknowns in xi and k plus k dash unknown in lambda r. Now, degree of freedom. Now, what is degree of freedom? The minimum number of independent variables u1, u2, un required to fix the position and configuration of a dynamical system which are compatible with the given constraint is called the number of degree of freedom of the system. So, degree of freedom is actually the minimum number of independent variables required to fix the position and configuration of a dynamical system. For a particle in three-dimensional motion, we have 3 degrees of freedom. One is corresponding to motion in x direction, one is corresponding to motion in y direction, and one is for the motion along z direction. For a system of n free particle, degree of freedom is 3n, and if there are n particles with k constraint, then the degree of freedom will be 3n minus k. This k is constraint and n is number of particles. 3 point masses connected by 3 rigid massless rods is showing here. So 1, 2 and 3. There are 3 point masses, and these point masses are connected with 3 rigid massless rod. So n equals to 3 and k equals to 3, because here we have 3 constraints. So degree of freedom is 3 into 3 minus 3, that is 6. So degree of freedom for 3-point masses connected by 3 rigid massless rod is 6. Now, for a rigid box having n is greater than or equal to 3, that is, the number of particles for a rigid body are 3 or more than 3, then the degree of freedom for this rigid body will be 6. A rigid body fixed at one point have degree of freedom 6 minus 3, that is 3. The body can rotate freely about this fixed point with these degree of freedom. A rigid body rotating about a fixed axis in space have degree of freedom only 1. Now, generalized coordinate. So, generalized coordinate for a system of n particle with k independent constraint, degree of freedom is 3n minus k, and this is always less than the total number of Cartesian coordinate, because for a system of n particle the Cartesian coordinates are 3n. So we choose any 3n minus k Cartesian coordinate to the independent variable out of 3n, because the total number of Cartesian coordinate for a system of n particle is 3n. So we can easily choose any 3n minus k Cartesian coordinate to the independent variable out of 3n. So we choose q1, q2, qn independent quantities such that all Cartesian coordinates are known function of qi variables. So x1 will be function of q1, q2, qn and t. In the same way, x2 will be function of q1, q2, qn and t, and xi will be function of q1, q2, qn and t. It means every Cartesian coordinate will be function of q1, q2, qn and t. In the same way, Cartesian coordinate x3n will be function of q1, q2, qn and t. This system is called rheonomic if some or all of the above functions are time. Otherwise, the system is called scleronomic. The variable defined by previous equations are called generalized coordinate. Thus, generalized coordinates are independent coordinates sufficient to completely specify the configuration of a dynamical system. The generalized coordinate can be in other coordinate system. For example, if a particle revolves around a fixed attracting center, then the generalized coordinates are in spherical coordinate system. Now, in spherical polar coordinate system, x is r sin theta cos phi, y equals to r sin theta sin phi and z equals to r cos theta. So these are the coordinates in a spherical polar coordinate system. Now, here we end our session. In current session, we have discussed about Lagrangian equation in generalized coordinate, degree of freedom, and also about generalized coordinate. So, goodbye.